I can't share the screen. It says I need permission.
And now you should be able to share your screen.
Yeah. Do you see my slides?
Yes, perfect.
So let me sort out these windows.
So if you're ready, the screen's yours.
Okay. Yeah. So I guess I'm hoping to speak to about 30, 35 minutes, maybe 45, speak slowly, which I sometimes do. And that should give plenty of time for questions. And that's the best thing, even though we are remote. I think I'd like to engage you in conversation and discussion. So this work is all about making things faster, but the proposition is that when you make things much faster, like 1 million times faster, then you can learn new things because you extend the capability. You can simulate things that you couldn't do before. So the topic is atomistic modeling. So within materials modeling, there are many, many length scales. And of course, you see the whole spectrum here, all the way from quantum chemistry, which is essentially sort of exact. And to the extent it isn't, it becomes a little bit of a philosophical debate. But the next length scale down is 6 orders of magnitude lower than angstroms and femtoseconds. So we can take quantum chemistry as exact and work ourselves up from there. And that is sort of the topic that's called first principles modeling, where each of these methods you base on the lower one. You define density functionals by solving the exact Schrödinger equation for smaller systems for the electron gas and so on. And then you can try and make tight binding models based on density functional theory and so on. You can make coarse-grained force fields based on real force fields. But actually, when people talk about first principles modeling, typically that kind of ends at the electronic structure level. And the rest of it, when you go to higher up, typically it's kind of a mishmash of bottom-up modeling and top-down modeling. So typical empirical force fields are partly based on electronic structure data, but then partly fitted to experiment that you measure in the lab. So spectroscopy, solvation free energy, and other thermophysical properties of molecules. So what we are trying to do with ML techniques is to just directly extend first principles modeling to the level of force fields, to thousands, 10,000s, perhaps 1 million atoms, and to go for many, many nanoseconds. Nanosecond simulations should be routine. If you have an enormous computer and run for a very long time, you should be able to do hundreds of nanoseconds. And so the idea is that these are you retain the accuracy of the underlying electronic structure method, but you speed it up. And I put factor of 1 million here, but it could be bigger because quantum mechanical methods scale poorly, whereas force fields scale linearly with system size. So if you take the bigger systems, the scaling is better. So just to set the scene of density functional theory, it really is I will talk a lot about that because that's where most of our data is coming from. And that's been really the workhorse of materials modeling for the past 30 years. I won't go into the details of these applications, but you might know one or the other or all of them very well. You can do phase diagrams in extreme conditions where you can't do experiments. Here's the phase diagram of carbon, for example. Aqueous solutions of polyatomic ions, again, is a very complex system from an atomistic simulation point of view, and experiments cannot access the detailed structural and dynamical properties on the atomic scale. But density functional theory has been validated and then used to understand that. Surface science is a huge area where electronic structure methods have complemented experiment for a very long time. This is a titanium oxide surface with molecules on top, where the microscopy, even under UHV microscopy, doesn't quite get to the atomic scale to investigate bonding and reactions and barriers. But when you run electronic structure simulations, DFT, MD, or DFT reaction discovery, then you can figure out what happens. And a whole lot of nanoscience, as it's now typically called, but of course it was a lot of activity happened in the last 20, 30 years on carbon structures. Here's a forest of aligned carbon nanotubes, and the way these nanotubes are grown has been extensively studied and simulated with DFT, or in conjunction, hand-to-hand, in hand-to-hand experiment. Before I describe the ML methods that we apply here, I just want to make the point that that machine learning, and generally AI for science, is a really, really good field to be in, because while the traditional ML and AI solves problems that we already know how to solve, just makes them cheaper, and the just is of course not to underestimate the economic effects, right? So once you have self-driving cars, it will change the world, it will change our society, but it doesn't extend knowledge in a way, it doesn't extend human science. We already know how to drive a car. But when you apply ML to science, you can do things that you couldn't do before. So it's not just an economic proposition. Because of the very large factors by which you do the acceleration, you can do things that have been entirely intractable or impractical before. So if you're thinking about soft systems, drug discovery, for example, if you make an ML system that can tell you whether a drug molecule binds to a protein, you can screen on a scale on which you couldn't screen before, because experiments have to be done, and they are much more they're very, very expensive. So you could only screen many fewer compounds experimentally than you can computationally. Or something that we've done already in the material space is you can simulate 100,000 or 1,000,000 atoms with electronic structure accuracy, DFT accuracy, and observe things that you couldn't observe before. So, and this is the longer term vision, not really mine, but of the whole field, is that you inject AI-driven simulations into the discovery loop of material science. So you can generate structures, and perhaps you can do those with classical methods or with ML-based methods. You can simulate their properties on a large scale in very complex setups that you couldn't do before. And then you can test them in the laboratory. And lots of groups are engaged in using ML and AI to enhance laboratory testing and automated labs. I don't do that, but it's a very big area. And of course, you go around in that loop. So how do we build first principles force fields? We need some kind of representation of the atoms. And that's, we used to do them with some sort of description, atomistic geometrical description. Nowadays, that's all built in and combined with the regression. But if you use descriptors, then given those descriptors, you use some kind of regression method to fit a function of those descriptors. And Gaussian process regression is where we started, but linear regression or neural network regressors are also very, very prevalent now. And then you can regress many, many different atomistic properties, NMR chemical shielding tensors, polarizability, for example. But what I want to focus on now is force fields. So when you regress the atomic energy and the forces that you compute with electronic structure theory. So you need data to do this regression. So you do electronic structure simulations on a size scale where those are feasible, because of the much worse than linear scaling. Depending on the method, this could be dozens of atoms or hundreds of atoms in the case of DFT, for example. And then that gives you points on the potential energy surface. And with your representation and regression, you essentially come up with an interpolant of the potential energy surface, which you can go and test and validate extensively. And if it's good enough, you use it. If it's not, you go back and get more data. And a huge amount of work was done over the past 10, 15 years on how to do that efficiently and effectively. It's typically called iterative training or active learning. Let me show you a couple of examples. So this is work by Volker Deringer, who was a research fellow in my group, now professor in Oxford, where he's using the atomic cluster expansion. It's a linear fitting, it's a linear basis for creating interatomic potentials. And he's simulating phase change memory here. So it's germanium antimony telluride, GST. This is the geometry of the real device. You have a couple of million atoms here. And well, actually, in this case, tens of millions, but he's selecting a slice. So it's 100 nanometer by 100 nanometer block. He's selecting a slice from this. And then in this sort of quasi-2D geometry, applying a heat pulse, and the phase change memory can go from crystalline to amorphous and back. And I mean, this is just the highlight. Of course, there's lots and lots of validation work was done. But you can see that we can reach these length scales and time scales that are necessary. So with the ACE method, you can have 1 million atoms and simulate them for nearly 1 million time steps per day, and observe the processes that happen in this device in kind of real time. And what they're doing here is applying 2 different heat pulses, and this is the amorphous state, the yellow. And then as you apply the heat pulse, there is of a certain intensity and time duration, you get recrystallization. And what they're showing here is that depending on what kind of pulse they apply, you can control the amount of recrystallization. And you see the polycrystalline outcome at the end. So while we were using ACE up to a couple of years ago, it was a very fast method, a kind of a synthesis of previously proposed ML schemes, and was written down by Ralph Trouts in 2019. And as I said, it's based on this complete linear invariant basis for atomistic geometry. We moved on in about 2022, mostly the work of my graduate student, Ilyas Batatia, who takes the local description in terms of a radial basis R and YLM of a neighborhood of an atom. We form 4-body descriptors. Out of those, ACE in principle allows arbitrary body order, but it's enough to form these 4-body descriptors. You create these ACE descriptions around each atom, and then you pass that description around. Every atom hands the description to its neighbor. That's called message passing. And then you do it again. Then you re-expand those past, the messages you receive in the 4-body truncated linear invariant basis. And that is essentially MACE. Don't try to read the equations on this screen. They're in the papers. But that is essentially what's going on. What I quite like about this formalism is that we can write down the equations and go through one by one and understand the functional form that we're fitting. But at the same time, this is fit with the techniques of modern ML and deep learning. Essentially, another name for this is equivariant graph neural networks. Right? Equivariant because we have scalars, vectors, tensors, and so on that comes directly out of ACE. And graph because we pass them around to the neighboring atoms, and neural networks because we fit. This is a nonlinear fit. There are lots of degrees of freedom at each of these stages in these equations, and so we fit them with the techniques of neural network fitting, stochastic gradient descent, and so on. And many of the one-dimensional functions that are involved, for example, these R's here, R and L, are actually actual artificial neural networks. They are just feed-forward multi-layer perceptrons. But there's a lot of deep geometry here. So, for example, in this paper, Delarose and colleagues in 2025 have proven that this construction of four-body local representations passed around once and re-expanded gives you a description of the geometry which is unique. So you can reconstruct each atomic environment. To my knowledge, this is the only proof that exists of this only proof that there's one kind of descriptor for which it is proven that you can reconstruct. ACE is a complete basis if you don't truncate it. So if you go to arbitrary body order, then of course it's complete, but no truncated version actually is proven to be enough to reconstruct the local geometry. So MACE has been, so this is called MACE, and it's been used as one of the most accurate force fields now. And the same kind of iterative training has been used in the last 5 years to build up models for particular materials for any particular project. But what I want to tell you about is what happens when you try to make a universal model. So you fit all materials at the same time. So the data isn't made specifically for this, wasn't at the first time. It comes from the Materials Project, which is a 20-year-old, more than 20-year-old project to document and record in a reusable way DFT calculations that people do. So by now it has 200,000 materials. Only about 50,000 of them are real materials that have been made in the lab and you can hold in your hand. But the other 150,000 are DFT calculations of proposed materials, local minima, different phases that are higher energy, higher pressure temperature phases. But it's a very well curated repository. So in 2023, the students behind the Materials Project have started playing with our model and fitted a MACE to all the material that was in the Materials Project at the time. And really the purpose of this leaderboard, and this is the model that was fitted, MACE MP0, and this was the date of it is 2023. And the point is of the Materials Project, and these fits at the time, was to predict the energy and stability of new materials. So the test here, and much of these correlated metrics, these are the F1 score, the precision, the MAE, the R-squared, they're all about trying to predict the stability of a new material on the convex hull. And when MACE was first fitted, it gave a real jump in performance. So if you look at, again, the dates, the 2022 M3GNet was the previous best model. And the score in predicting the CPS score is some combined performance score in performance of this model, and it kind of doubled. And that result gave rise to a huge flurry of activity starting in mid-2023, and you can see the result at this recent snapshot. So now there are many, many more recent models that do much, much better and nearly saturate this benchmark of, again, measuring the energy accuracy for a withheld test set in this materials database. But really the question that I was fascinated by is how physical and ultimately useful are these models for simulation? So rather than just predicting the energy of a new small inorganic crystal, what can you actually use these models for? And that was a huge, huge surprise, that almost accidental discovery that these models are very useful. So here's a little movie of what's in the database, training database. So small inorganic crystals, typically 10, 20 atoms big. I think 70% is less than 20 atoms, 90% is less than 50 atoms. And then you take this model and you just simulate whatever material system occurs to you. And my group did that. Every student was told to stop whatever they were doing and take whatever structure was on their computer screen and simulate that. So we have simulation of battery electrodes in contact with electrolyte, copper, graphite, flakes, and so on, to perovskites, to aqueous interfaces, of salts to polymerization of sulfur rings, amorphous carbon, combustion of hydrogen, heterogeneous catalysis, and so on, anything that you can think of. And the astonishing observation was that the model trained on small inorganic crystals was stable at high temperature MD in all of these materials, and roughly the right things happened. Hydrogen got combusted, heterogeneous catalysis happened with typically reasonable barriers, and salt dissolved in water in approximately the right mechanism, and so on. And before that, before these equivariant graph neural networks, before the Mace model, this was not the case. So you couldn't take a model fitted on small crystals and go and do materials chemistry with it. So that's the big news, and it really changes the workflow of how people simulate materials. And the associated paper was a huge amount of fun to write. So this is a paper with 88 authors, everybody contributing one of these examples in a sort of 100-page supplementary where we describe the application to each material system and show that it's approximately reasonable. So here's a little graphical history of essentially summarizing what I said before. So before 2007, before the seminal work of Baylor and Parinello, of course, people have used ML-type techniques, neural networks to fit potentials, but only very low dimensional fits were made for very small molecules. And of course, you really understand what's going on. You have 2 or 3 dimensions and you fit a function, but that doesn't really give rise to new kinds of simulations. Beginning in 2007 is this intervening, this sort of 10, 12 years of iterative fitting, and the idea that with good descriptors, you can make models for bespoke models for given materials. And if you have data everywhere, then you can interpolate that data, and where you don't have data, the models were rubbish. So very poor extrapolation behavior, but locally very accurate. And then the foundation models are where you train on a relatively small part of configuration space, and your model is quite reasonable everywhere. And we call them foundational models because if you want a simulation to be very accurate for a particular model, and you determine that out of the box it isn't, then you just take a little bit of new data there, not very much, and you fine tune. You adjust the model parameters a little bit. It takes a few hours on a GPU to do that, and then your model is very accurate there while retaining this sort of approximate accuracy everywhere else. So high accuracy with fine-tuning, still good extrapolation, and high transferability. To be honest, we don't really understand why the extrapolation is so good. So that's one of the things that's kind of keeps me up at night, is what is it in the structure of these models? What is being learned here? We don't know. So just sort of summary statistics. So we can routinely do thousands to millions of atoms, depending on the number of GPUs you have, tens of nanoseconds, and then when fine-tuned, you can have ab initio accuracy. The training of such a model is not cheap, but it's not insanely expensive. So 20,000 hours, at sort of market rates, that's $50,000 in real money if you want to buy the GPUs on the open market. And of course, now a huge number of people are engaged in making these models, refining them, and figuring out traveling the Pareto front of accuracy versus efficiency. And yeah, we don't know why they work. So let me give you a few more examples on what we can do for organic systems, because while material models and different versions of DFT are sort of queuing up to enter into ML heaven in terms of materials modeling, biosimulations and organic systems are a very different business. So all these models are much more expensive than empirical force fields, 100 times more expensive, and much of biomolecular modeling is limited by timescale, not by accuracy. So it's been much slower to enter the field of organic chemistry than materials chemistry. Let me mention 3 tasks that are hard in the drug discovery space. This work is done in Angstrom AI, which is a Silicon Valley startup that tries to adapt these techniques to the drug discovery process. One of them is solubility. So you can think about small molecules and try to calculate their solubility in water and in fat. And that's one of the tasks that you need to do when you propose a drug molecule quite early on. You want the solubility to be not too high and not too low. And of course, experiments for several $100s. Once you make the molecule, standard experiments can tell you. A second one is organic crystal structure prediction. So if you are proposing a drug, you need a small molecule drug, you need to know the polymorphs that it's going to crystallize in, because that's how you're going to eat the drug and its crystalline powder, crystalline form. And of course, the big one is protein ligand binding. So does it actually bind? Does a drug molecule bind to a protein and interact with it? Again, not too strongly and not too weakly. So for solubility, I think we're doing very well. So here's a sort of an early example of a MACE model fitted to a set of small molecules, nothing to do with solubility. It's just molecules in vacuum. It was called the SPICE dataset, and MACE-OFF was the first model we made. And then we calculate the hydration-free energy. So big box of water, alchemical transformation, and you get the experimental result back, basically. So blue is experiment, green is the model. And empirical force fields don't typically do super well in this task, even though they've been fitted to solubility data. These are 2 sort of standard models. And when you go to fat solubility, so typically the way this is measured is the difference between the partition coefficients, the difference between fat solubility and water solubility. The empirical models do much worse. And the MACE model gives you back essentially the experimental result within the error bar of experiment. Moving on to crystal structure prediction, this is where we need to make specialized models. So these are not the same model that we use for hydration and solubility, but you take small molecules. These are not yet drug molecule size, but just very small molecules which have standard crystals that have been sort of accurately characterized. And we focus on modeling the intermolecular energy, and the red bar here is in sort of milli-eV per atom, the intermolecular energy accuracy of this MACE-OFF model, the one with which we did the hydration. And that's not really, these errors are not really good enough to distinguish between polymorphs, because intermolecular energies are much smaller. But if you make a bespoke model that targets the intermolecular energy, then you can get these very, very small errors. The left side is a test set on a Cambridge structural database, so a large experimental test set. And on the right, I show the test set of actually on drug type compounds from the blind tests over the years. People set up a challenge to predict drug crystal structures. And for these blind tests, we can also see if we get the lowest energy structure to be the one that they see in experiment. And here, the baseline is DFT. It's expensive, but this is how people do it. This is how drug companies try to predict the stability of the crystals of new compounds. And this is a particular flavor of DFT that does reasonably well. And these are the blind test compounds. And you can see that with the MACE model that's specifically made for crystal structure prediction, you almost recover the accuracy, except for 1 or 2 places, what DFT would give for the ranking, where rank 1 means that you get the lowest energy structure equal to the experimentally seen structure. So the biggest limitation of the models that I've mentioned up to now is that they don't have electrostatics and spin explicitly. The universal models are short range. And that is not quite good enough, especially for organic modeling. The electrons have been completely eliminated, and that's why they're fast. And I think people broadly agree that we sort of need them back a little bit if you want to do magnetism, if you want to do long-range electrostatics interactions, which are weak but important, for example, in the crystal structure prediction problem, or at interfaces, then we need this coarse-grained description of electrons back. And this is, of course, not a new idea, right? So many people have done this in some ad hoc way. And what we hope to do by explicitly considering charge and spin and doing self-consistent electrostatics is that even the energy, not just the electric response will be better, but models will be simpler and more transferable. So here's our first attempt at this. So this is based on a new data set called OMOL 25, which was made by Faircam, the sort of division of Facebook that does chemistry for unknown reasons. It's about 100 million molecules up to size 300 computed with a very high level DFT. Now it's been extended to 140 million just recently. And of course, we are recomputing our models, but we've made a polarizable model based on this. So it starts with MACE, the two layers of ACE expansion, but then in addition to that, then we predict multiple moments, and from the multiple moments, we get a field. From the field, we recompute the multiple moments. So we predict new updates to multiple moments based on the local field, and we do this twice and get, and the final multiple moments are then used to compute electrostatics and the correction to the energy based on the field features, field and multiple features. So that's the essence of the model. It has electrostatics explicitly built in. When you go from the predicted multiples to the field, you solve the Poisson equation. And when you do this, things on this OMOL type fit, and you test it on difficult problems, things dramatically improve. So for molecular crystals, this is now a much larger set of crystals than what I've shown before, and you see these cyan colors are the two different versions, medium and large, of this polarizable model. And the other models are also trained on OMOL, but don't have explicit electrostatics in them, and you get a dramatic improvement. Another very stringent test is bulk water density. And remember, this model is only trained on clusters, including water clusters, and its density is about, at room temperature and pressure, it's about 1.08 grams. It's 8% too dense. And that is a very generic result. Every organic liquid is too dense with all of these models. So UMA model that's trained by Facebook. MACE OMOL is a non-electrostatic, and MACE Polar is the electrostatic model that we made. They all overestimate densities, and this is the consensus, although it's very hard to prove, but the consensus is that this is the prediction from this functional, this omega B97 MV functional just gives you a water density, organic density that's too high. But regardless, the polarizable model gives qualitatively the right result when other models don't. So here's, again, a very hard test for this sort of thing, where you have a pair of chlorine atoms in two water clusters that are separated, and if you do it neutral, then you should get two Cl2 molecules. If you put two electrons into the combined system, then those two electrons should go into the chlorine, make two chloride atoms, which should then separate, and the other pair of chlorine atoms should still form the Cl2, and that's what happens if you run this with DFT. If you run it with the non-electrostatic model, no matter how accurate, then there is charge transfer, a small amount of charge transfer between these two clusters that shouldn't happen, and both of these, all four chlorine atoms separate. And when you do this with a polarizable model, then this doesn't happen. So you don't get the charge transfer between the clusters. You correctly recover the fact that one of the Cl pairs separates, the other one doesn't. We're also moving into a more explicitly self-consistent model where you don't just do 2 iterations of charge distribution, but actually run that loop to full self-consistency. And when you do that, you can do cool things like interfaces, metal insulating interfaces. Here's a model that's trained on an aluminum slab and external fields, and separately on a water slab and external field. And when you put the 2 together and put an electric field on, you see the correct behavior. So you see the electric field here, the metal is conducting, so no field, and then you see the reduced field in the water, where the electrons polarize a little bit. You have a dielectric constant of 1.8. So you get a reduced slope before you get back to the full slope of the full electric field in the vacuum. And this is what I'm showing you here is the charge density. And of course, the charge density is not reproducing DFT. That's not what we want. DFT has a very complex charge density profile as it moves close to atomic nuclei. And we don't want the full detail of the electrons, just the coarse grain description. But we see the physically correct behavior of a surface charge, which is smeared out. It's not as sharp as with DFT. That is the result that we want. And then here's a different offshoot. So that's putting magnetism in. And for now, these are separate, but eventually, of course, you want to put them together. You take MACE and you put vectorial inputs on each atom. So they represent a vectorial spin that sits on each side. You have to be careful about the rotational symmetry because now if you apply a rotation Q to the entire system, you want to recover the invariance of the total energy with respect to a global rotation that rotates the geometry and the spin. If you have no spin-orbit coupling, then you can rotate the spins and the positions separately. So you rotate the positions with Q, the spins with Q prime, and you should still get the same energy. But if you have spin-orbit coupling, then this larger symmetry doesn't apply. So this is not too hard to implement. And then you can study exotic systems, like here's a manganese platinum M3PT, and you see the non-collinear spin relaxation, and this is the frustrated magnet, really, and you see this sort of triangular arrangement of spins as you optimize the energy with respect to the spin direction. You can do larger scale simulations like the Curie temperature of iron. Now, this has been studied for a long time with effective models. So on the left, I'm showing Ising model simulations where the J couplings between the neighboring spins is extracted from density functional theory using various ways. And of course, all of them tell you that this is a magnet with a ferromagnet with a Curie temperature, but it's not very predictive. You can see that depending on how you extract those J couplings, and this is not just nearest neighbor, but a few hops away, you get completely different Curie temperatures. And when you do a direct simulation, so this is basically taking the MACE model fitted to iron DFT data with explicit spins, that's the blue line, you get sort of with this magnetic MACE model, you basically get the Curie temperature that you should be getting, which is about 1,000 K. There's a literature value, one of the literature values also. When you do this with ACE, then you also get the same answer. So what's next? We want to make an electrostatic material model, and the reason that we haven't yet is lack of data. So the large materials databases, for example, Materials Project and things derived from that, haven't saved the charge density. It's a small oversight on behalf of those data providers, but that's what's really needed to fit an electrostatic model. And then combining materials and molecules, which is where, if you want to do catalysis, for example, or battery electrodes, electrolyte systems, on a basis of universal foundation models, we need to think very carefully about the level of electronic structure. So what kind of electronic structure theory describes materials very well and molecules sufficiently well? This is a very tough problem. For example, the omega B97 MV functional, which we used for the polarizable organic model that was used to make the OMO data set, doesn't converge from metals. The exact exchange is a Hartree-Fock-like exchange, and that's just the wrong theory for metallic systems. So this is really an outstanding problem. So yeah, thanks very much. I'll stop here, and very happy to engage you.